In this problem, we're looking at a new type of three-dimensional figure called a truncated cone. Now, the word cone is in the name of this 3D figure for a reason. It has many qualities very similar to a cone, and we're actually going to use the knowledge we have about cones to figure out the problem for a truncated cone. So, a truncated cone is just a portion of a cone where you've made a cut between the base and the vertex. So imagine like an ice cream cone, and if you were to just cut it right in half. So that new portion of the cone would have two circular bases, the original kind of base, and then the smaller base, and the connected portion. And it would no longer come down to a vertex like in the original cone. In this example I have here, I list, if you've seen the movie Up, this is the dog from Up who wears what they call the cone of shame. And you can see here that it is a truncated cone. There's the larger circle, which would have been the base of the original cone, around its head, and the smaller circle around the neck. If it would extend out to an actual cone, it wouldn't fit on the head. We also have things like lampshades, which often look like truncated cones, where it has that bigger base and it comes to a smaller base up top, and then there's the open area. It doesn't go to a vertex. That's a truncated cone. Now, to solve this problem, we're going to look at similar triangles. And I'll show you in a second where those similar triangles come from. But by using our knowledge of similar triangles, we're going to get all the important pieces of information about a truncated cone to figure out the surface area and the volume. So here I've drawn out the actual kind of mathematical diagram, or a mathematical diagram of a truncated cone. It's just the blue portion of the cone. So you see the bottom circle is bigger and the top circle is smaller. So that's the original base and now the other base. But this dotted line here coming up to the point A is very important. You'll notice if you think of the bottom circle extending up to A, that would be one large cone. And that's going to be really important. But then you'll also notice we have a smaller cone. If you look at the circle here, where we have B as the center, this smaller circle up to A would be in another cone, where it's a circular base going up to a vertex. So we have a large cone, a small cone, and then the truncated cone, which is the actual figure that we're trying to figure out. In this problem, I've given you three pieces of information. I've given you the large radius, which is DE, which is 6. The small radius is BC, which is 4. And then the height of the truncated cone is 6. That is BD right here. So I'm going to show you where we get these similar triangles. This purple triangle right here is the triangle formed between the center of the larger circle, a point on the outside of that circle, so DE is then a radius, and then the vertex of the cone. I'm going to scoot it over here. This green triangle is formed with the same pieces of the smaller cone. So the bottom of the triangle makes up that radius, and then we have the height of that smaller cone, and then that slant height, B, C, and A. So I'm going to scoot that over here. Now, similar triangles have all of their angle measurements equal to each other. And you could probably verify for yourself if that is true. They both clearly have a right angle at ABC and ADE. And then clearly angle A is the same for both. And then we can get that angle DEC and BCA are equal if we look at our transversal knowledge. That's not super important for this problem. The important part of the problem is that these are similar triangles, and you can verify that by looking at the angles. And that is going to give us what we need to solve for the information we don't have. So we want to find the length of AB, which is the height of the smaller removed cone. When I say the smaller removed cone, that is the smaller circle base up to A, which we can represent with this smaller triangle. So that would actually be this height right here on the triangle. We don't know that. What do we know? Let's transfer what we know to these triangles over here. So DE is the big radius, and that is 6. So I'm going to write that right in the radius, or the bottom of this triangle that represents the big cone. The small radius is 4. That'll go over here. And then the height of the truncated cone is 6. Now, is the height of the truncated cone one of the sides of either of these triangles? No, it's actually not. You'll notice that this bigger triangle goes from A to D, and the smaller triangle goes from B to A. So we have this knowledge right here, but we can't write that down anywhere. So we got to do a little workaround to get there. The first question wants to find AB, the height of the smaller removed cone. So we often call the value of something we don't know x, that's our variable, and we're going to do that here. So we're going to do AB, the height of the smaller removed cone, which is right here. We're going to call that x. So what is the same side length in the bigger triangle? Well, x was from A to B, and we know B to D is 6, so it is actually 6 plus x. Let me scoot that over a little bit so we're not covering the triangle. But that comes directly from the knowledge we had that BD is 6 and that missing variable or that missing number, which we called x. So usually in similar triangles, you can set up a proportion because you have two values that you know from one triangle, and the other triangle, you have one of the values and then one of the other values is missing. And you can set up a proportion and cross multiply. In this problem, we actually have two missing values. But because there's that related x in both the missing values, we can still set up the proportion as we would, and you'll see with a little algebra, we're able to solve for x just like we would hope to do in a normal problem. So let me go ahead and set up the little proportion here. If you give me a second, I'm going to have to draw little lines. It's a little hard with this writing software on the video platform, but that's okay. We'll figure it out. So what you do is you set up one of the side lengths on top for one triangle and the other side length on the bottom for that same triangle. So I'm going to start with this green triangle on the left side of this equation. So I'm going to do the radius on top, the radius of the circle, or what we can say the bottom side length here on top. So that'll be 4 for the green triangle. And then down in the bottom, it's that height, which is x for us. So let's go over to the other side. You then set up the same side lengths for the other triangle. So this right side is now going to be our purple triangle. So what was our bottom? Well, over here it is 6. So we're going to write 6 right there. And what was the height of that triangle right here? It was 6 plus x. So when we do these problems, usually this is a proportion we can calculate by cross multiplying. And that's because with similar triangles, the ratio from one side length to the other of one of the triangles is the same ratio as the other. That's why we have an equality here. So we're going to go ahead and do the same thing and cross multiply, which I'll draw in here with some little arrows so we remember. Multiply the top of one side to the bottom of the other, and the top of the other to the bottom of the original side. So what we're going to get now is we're going to get 4 times 6 plus x on the left, and that's going to equal 6x. So here we have a pretty basic equation. So all we need to use is our algebra skills to get at x, and that's going to give us both the height of this green triangle and the height of the purple triangle. So first step, we're going to distribute through because we want x alone. So that's the first step. We're going to do 24 plus 4x equals 6x. Then what we want to do is we want x alone. So again, we've got to get x to one side. So what I'm going to do is I'm going to subtract 4x from both sides, and then I'll get 24 alone on the left side. So we're going to get 24 equals, it'd be 6x minus 4x over here. That's just 2x. Final step, just divide by 2, and that will give us 12 equals x. So as you can see, even though we only knew 2 of the side lengths, because we had x in both of the parts of the missing side lengths, we were able to use a little algebra to solve for x. So now that gives us very important information. First, x is 12, and that is actually the first question. What is the length of AB, the height of the smaller cone? That's going to be 12. The next question is what is the length of AD, the height of the full cone? That's just asking what is the height of this purple triangle. And that's 6 plus x. We know x is 12. 6 plus 12 is 18. So that will be 18. So now the next two questions, I'm not going to solve for them because you know how to do it, but I'm going to give you the hint. It wants the slant height of the smaller cone and the slant height of the full cone. That's really asking you to find the diagonal of this green triangle and the diagonal of the purple triangle. What are you going to do to find that? Your handy dandy Pythagorean theorem, because these are right triangles due to these right angle symbols right here. So that's how you're going to figure out these two problems. Now, I'm sorry, these pictures are going to cover the words a little bit, but just so we can talk, I'll scroll up so it's a little clearer. But the next part says, what is the lateral surface area of the smaller removed cone? And what is the lateral surface area of the full cone? And then given the last two answers, what is the lateral surface area of the truncated cone? So now that we have the information we need for the smaller cone and the larger cone, you can solve for the lateral surface area of those just like you normally would. you can find the lateral surface area of the smaller cone and the lateral surface area of the larger cone. So then you have that curved surface and the full curved surface, and you want this leftover bit. So all you need to do is just subtract. Take the full lateral surface area minus the lateral surface area of the smaller cone, and that'll give you the lateral surface area of the truncated cone, that part of the blue figure we're seeing there. The next part says, what is the surface area of both of the bases of the truncated cone combined? Because remember, for total surface area, we want the area of every surface on the figure we're looking at. So in this blue figure, we already found the lateral surface area. So now we have these two circles. You can find the area of the circle. I know you can. Just use the radii that you have for DE and BC. And when you can add those all together, that will give you the total surface area of the truncated cone right here. The last part is, what is the volume of the truncated cone? Again, I'm not doing these calculations because I know you've done this in previous problems, but just giving you a setup so that you know how to do it. For the volume of the truncated cone, you're going to do a very similar thing for what you did with the lateral surface area. You're going to find the volume of the full original cone using the information from this purple triangle, and subtract the volume of the smaller cone, the removed portion, using the information from the green triangle, and that will give you this leftover space, because you had the space of everything combined and then the space you removed, and that's the space you want. So that's how you're going to approach this problem. It's a long problem. There's many steps, but really the most difficult part of this problem is working with these similar triangles to figure out what x is. Once you have x, it's just a lot of similar things which you've done before, but just several parts of it. If you have more questions, feel free to reach out. We'll give you some more help, but I think you can do it. Good luck.